Okay, welcome to section 2.1, rates of change and limits. I'll try to make this section a little bit shorter than some of your other videos. So suppose a function f is defined on an interval around x equals a, but not necessarily at x equals a. So you could have a hole at x equals a, could have a vertical asymptote, doesn't matter. If the limit exists at x equals a, as x becomes closer and closer to that a value, your y values become arbitrarily close to some value L. And we write this as the limit as x goes to a of f of x equals L. So down here we have this here what your x values are doing. They're getting closer and closer to a. Then the limit equals whatever your y value is approaching. So you can see here the limit of your f of x values, which are your y values, equals L. Doesn't necessarily get to it. Sometimes it does, sometimes it doesn't, but that's what its limiting value is L. Two important formulas to know: average rate of change, and I always abbreviate it AROC because it's just very long, equals, my deltas didn't work, delta y over delta x, right? Change in y over change in x, which is the same thing as f of x2 minus f of x1, all divided by x2 minus x1. And the second one is instantaneous rate of change. This one looks a little bit more complicated, but it's very similar to this one. I'll talk about that in a minute, but it's the limit as h goes to 0 of f of a plus h minus f of a all over h. So instantaneous rate of change would tell us what the speed would be at a particular time. Average rate of change would be over a certain time interval, what the average rate of change is, so what your average speed would be. Example, a ball dropped from rest from the top of a tall building falls y equals 16 t squared feet in the first t seconds. So this is the distance that it falls, y, and t is measured in seconds. And all of these questions have to do with the speed, so that has to do with your change in y over change in x. Okay, I can't just be plugging values into here. So find the average speed from 3 to 6 seconds after the ball has been dropped. So average speed, we're looking at my average rate of change equation, or formula, which is change in y over change in t, right? The change in height divided by the change in time. So we want to look at the height after 6 seconds minus the height after 3 seconds. So plug 6 into the function, right? My f of 6 is 16 times 6 squared minus 16 times 3 squared divided by our change in time, which is 6 minus 3. And instead of writing all of these steps out for you, we get 144 if you evaluate in your calculator. And what about your units? Well, your change in y is being measured in feet, and your change in time is being measured in seconds. And we are dividing those, so it is feet per second, which makes sense because we were talking about speed, that it would be measured in feet per second. Find the average speed during the first 6 seconds of fall. So here we were doing 3 to 6 seconds. Now we want to do the first full 6 seconds. So it's change in y over change in t again, because it's the average. And now we're comparing it to 0. So we have our f of 6, which is 16 times 6 squared, just like before, minus f of 0, which is 16 times 0 squared, divided by 6 minus 0. And I went ahead and did that one as well, so we don't have to write it all out. And you get 96 feet per second. Alright, well that makes sense. If we think about it, during the first 6 seconds, right, the average was 96 feet per second. And during that second half of it, the 3 to 6 seconds, the average is faster, well, because the ball is going to speed up as it's going further and further down, because of gravity, of course. And we're looking at speed and not velocity. If it was velocity, then this would be negative. So speed is just the absolute value of the velocity. C. So let's find the speed of the ball exactly 6 seconds after being dropped. Exactly 6 seconds means we are looking at instantaneous rate of change, right? We're looking at a rate of change at a particular instance, not just the average over a time period. So I want the average, well, the instantaneous rate of change at 6, so I'm plugging in. My A value is 6. Okay. This is really just like the average rate of change formula, right? Is we still have this subtraction and the division and everything. Only instead of looking at 2 different values, I'm looking at 6 in this example, and a little bit more than 6. And I'm using 6 plus h to represent the x value a little bit more than 6. So this is f of x2, which is our 6 plus h, minus x1, f of x1, which is f of 6, divided by, well, our change in time, which would be 6 plus h minus 6, and then the 6's cancel, just leaving me with h. So that's where this formula is coming from. And then I just want my h to be as small as possible, so that's where this limit as h goes to 0 comes from. Okay, so really it's just average rate of change. I'm just looking at 1 point instead of 2. So, come down here again. So I have the limit as h goes to 0 of f of, well, I guess I won't have to write that part out, f of 6 plus h. So that's, everywhere I see t, I'm going to plug in 6 plus h. So I get 16 times 6 plus h squared minus 16 times 6 squared. Okay? That's my f of a plus h minus my f of a, all divided by 6 plus h minus 6, which is just 6. Okay, so now whenever I'm evaluating limits, all I want to do, right, the first thing I always want to try is, can I just plug in h equals 0? And no, I cannot. I will actually get 0 divided by 0. Okay? And that does not work. So we need to simplify this. Okay? So I have not taken the limit yet, so I'm going to keep writing lim as h goes to 0 over and over again until I actually take the limit. And I want to multiply all this stuff out, and then distribute my 16, and multiply that out, and so that I can cancel out my h's, and then I can actually plug in h equals 0. So, first thing I need to do is FOIL. 6 plus h squared is 36, plus 12h, plus h squared, minus 16 times 36, which is 576, all divided by h. Alright, and distribute the 16. Still haven't taken the limit. 16 times 36, well, I just did that with the 16 times 36, so that's 576. Plus 16 times 12, I don't think I've done that yet, plus 192, plus 16h squared, minus 176, 576, oh, doing real well. Okay, so already I can see that my 576s are going to cancel out. So let me grab a different color. 576 minus 576, which is fantastic. Oops, I forgot my H in there. That would mess me all up. It's wonderful that those two are canceled out because now everything in the numerator has an H in it. So I can rewrite this one more time. And I can factor out the h. And that'll leave me with 192 plus 16h. And I'll put the h in the front. And now we can see that h over h will cancel. And then everywhere I see h, now I can plug in h equals 0, because h goes to 0, so therefore everywhere I see h, I just plug in 0, and I get 192 plus 16 times 0, so that's just 192. And again, I'm dividing my change in y over change in x, which is change in the height divided by change in time, so it's feet per second. Let's just look at the other ones and make sure that this makes sense. Okay, it should be speeding up as it goes along. So since we're looking at exactly 6 seconds, okay, it should be even faster than this one. So 3 to 6 seconds, the average speed was 144. So at exactly 6 seconds, it should be higher than that because it's averaged with the 3 and the 4 and the 3.5 and 3.7 and everything in between. So therefore, it should be higher, and it is. Okay, next step, left and right hand limits. So a right hand limit is you're looking at the function as it comes from the right. So taking a look at this graph here, following my function from the right, my y value is going to 4. So therefore, the limit as x goes to 2 from the right, so goes to 1, sorry, goes to 1 from the right, so 1 with a little plus sign, of f of x of my function equals 4 in this example. And my left-hand limit as x goes to a from the left, so I would represent that as limit as x goes to 1 and then a little negative sign to show from the left of f of x equals 2. So that's my y value from the left, and my y value from the right is 4. And then two-sided limits. So these are the one-sided limits. I'm only coming at the y values from one direction. How does that relate to two-sided limits? A function f of x has a limit at x as x approaches a if and only if the right and left-hand limits at a exist and are equal, if they are the same thing. In other words, the limit as x goes to a equals L if and only if from the right it's L and from the left it's L. Let's do an example. So evaluate the following. All right, here I have a piecewise function. First question is saying, what is the limit as x goes to 2? Well, here's my x value of 2. And I'm approaching 2 from the right, so here's my function to the right of 2. So I'm following this function along. I'm going towards the x value of 2. And what is my y value approaching? That would be 8. And my limit as x goes to from the left. I'm following this side of my piecewise function equals whatever this y value is, which would be 4. And the limit as x goes to 2, that would have to be the same in order for it to exist as x goes to 2, and 8 is not equal to 4, so therefore this does not exist. Right. Notice for both of these, I never talked about what the y value actually was at that point. It was just what is it approaching, right? We're getting arbitrarily close to it, but not necessarily getting exactly to 2. So this last question asks us what it actually is the function. Well, at 2, my function is 6. So we get a 6 here. So from the left it's 8, well, from the right it's 8, from the left it's 4, therefore as we go to 2 it does not exist, but my function actually is 6 there, which is not equal to either of the limits, which is absolutely fine. And the last thing we need to discuss is the sandwich theorem. The sandwich theorem says that if I have a function f of x, and it's squished in between a g of x and an h of x function, then the limit, if I know that the limits of these functions that it's squished between, if I know that the limits as those go to a equals L, then the limit of the one of my f of x function is also L at x equals a. So let me draw a quick little picture. So if here is my f of x function, and I don't know what the limit of f of x is as it goes to a. I do know the limit of two other functions, so g of x, well, g of x would be below it. And h of x would be above it. So f is sandwiched in between h and g, and if I know the limit as g, limit of g of x as x goes to a is some value L, and the limit of h of x as x goes to a is also L, well then f, since it's squished in between those two, also has to go to L as x goes to a. That's all that says. So, example, we have sandwich theorem to prove sine of x over x. Okay. So in your notes, I actually took out this one, which can't really actually be proven using the sandwich theorem, which is unfortunate. But we will do the other one. So the limit as x goes to positive or negative infinity of sine of x over x equals 0. And we use this in class when we were doing limits. What do we already know about sine of x? Sine of x is always between -1 and 1, right? Sine and cosine are both always between -1 and 1 inclusive. And what I want to do is make it so that I have sine of x over x in the middle here, and then say what they're between. So in order to make that sine of x over x, I divide everything by x. So I get 1 over x is less than or equal to sine of x over x, which is less than or equal to 1 over x. And now I want to take the limit as x goes to positive or negative infinity. Well, I know what 1 over x looks like. Let's do that one first. So as I go to infinity, then my y value is going to 0. As I go to negative infinity, then my y value is going to 0 again. So therefore, I can say this goes to 0 as x goes to infinity, or negative infinity. I'll write them both. And new color, I have -1 over x, and it's going to do the same thing. As I go to infinity, my function is going to 0, and as I go to negative infinity, my function is still going to 0. So this function also goes to 0. And since sine of x over x is between -1 over x and positive 1 over x, well then this one must also go to 0, right? Because between 0 and 0, all we have is 0. So, sine of x over x, oh, I should write limit. So, limit as x goes to plus or minus infinity of sine of x over x equals 0. Okay. Makes sense. And that is it for me. Here is your homework, and I will see you tomorrow in class.